Okay, today we'll talk about the Amplus Law. So this is one of the four Maxwell equation. So in chapter 23, we already learned Gauss law, and this chapter we'll learn Amplus Law, and in the next chapter, we'll learn Faraday's law. So so Amplus Law and Faraday's law are about B field, and here it says that Amplus Law states that this is a line integration B dot ds equals mu naught I enclosed. So this symbol is looks the same as what we have seen in chapter 23 for the Gauss law. Actually, they are a bit different. So at that time, that is epsilon naught times integration of E dot dA equals Q enclosed. Actually, this is a surface integral. This is a line integral. For some of the textbook, this notation might be written as this one. So we have two integral signs to stand for, this is a surface integral rather than a single integral. But actually, this one is a single integral, and this is a line integral. Although it is a little bit different from what we have learned in calculus class, like f of x dx. So this one, we actually integrate f of x on the x-axis and then from a to b. But here we will try to define a path on the coordinate, so that so that we try to integrate the field along the path we defined. And actually this circle also means this is a closed contour or closed loop. So actually here, this circle means the path we define is a closed loop, or in the textbook it will call it Amplian loop. Okay, so the current I on the right side is the net current encircled by the loop. So let's see how we can use this Amplus law. So here on this figure, there are three current, I1, I2, I3. So you imagine this current is like it goes from negative infinity to infinity. So this is going out of the page, so it indicates by a dot. So this cross means this current is going into the page, and also I1 is going out of the page, or going out of the page. And you should imagine this current is from negative infinity to infinity. Okay, so and here is just show a cross section. So here we have I1, I2, and I3, and this orange line indicate the Amplus loop. Okay, so let's see. This is a line integral. What does it mean? So it is like in the space there are B field. The B field is not necessarily uniform, and for most of the cases it's not uniform. So so this is the path we define, and then we try to separate this path into many segments. So for each small segment, we can regard this this is straight. Okay, so this line is straight, and then ds is ds is actually the tangent line, and then follow the direction of the loop. Okay, so this is not only a line, but with a direction. You need to define it first. So for this one, it is somehow like counterclockwise. So ds point to that, point to upper right rather than lower left. Okay, so and also at this point, the B field is pointing to the top right. So in that case, for this segment, you can actually calculate B dot ds. because a b is just a vector, and then ds is also defined for this point. So you can calculate b dot ds for this part, and then also for next part, so on and so forth. And then finally, this one, so actually you can regard this is bi dsi, and this line integral actually means you try to add all those b dot ds or those inner product together, somehow like this. And of course, I tends to infinity, probably, yeah. The terms tends to infinity. So every segment is infinitely short. Okay, so that is about the line integral. And then for the right part, we have mu 0 I enclosed. Mu 0 I enclosed. So how to count I enclosed is that we can try to see this loop enclose I1 and I2. So let me just erase some of this stuff. Okay, so you can see enclose I1 and I2. I3 is out of the loop. So for I enclose, considering this loop, we only count I1 and I2. We don't count I3. And in that case, we also need to determine the sign of each current. So to determine the sign of the current, we also need to use the right-hand rule. Yeah, so you try to use your forefinger, follow the direction of this loop, like this. So somehow like this. So your thumb will point to this side, which means that this side is the positive direction. The direction pointing into the page is negative, which means that this current follows the right-hand rule. This is positive. So I1 is positive. And then our right-hand rule, positive is pointing out of the page. I2 is pointing into the page. So I2 is negative. I2 is negative. And then we don't count I3 because it is not in the loop. So we don't have I3 here for this one, for this Amperes loop. Okay, so this is pretty much it. So this one also tells you that this is out of the page, so you just use your finger, follow this direction. This is positive, this is negative, and then we don't count I3. Okay, so yeah. So yeah, so this is Amplus Law, and we can use Amplus Law to derive some good-looking formula, elegant formula. Okay, so this one and also this one. And actually you can see there are some, they are actually similar to each other. So this is the surface integral of the E field, this is the line integral of the B field, and then on the left side we can see epsilon naught, on the right side we can see mu naught, and this is Q, this is I, this is I. Q can generate E field, the charge can generate E field, current can generate E field. So yeah, so this is somehow a duality, and as I mentioned, for the duality, you usually try to exchange epsilon naught to 1 over mu naught rather than mu naught. So it should be a reciprocal of the mu naught. So this one we have epsilon naught on the left side, and then this one we have mu naught on the right side, which means that if you just move it to the left side, it is somehow like 1 over mu naught. Okay, so let's see. This one is what we derive in the previous lecture. So we use the Mps Law to really calculate this equation. Okay, so we really need some integration, and then using the Mps Law. So in here, we can also use the Amplus Law to verify this equation is correct. So for example here, this one is for outside straight wire. So here we have a straight wire, and then we assume the current is going out of the page. And actually we will assume the current is uniformly distributed for over the wire, but it only draw one dot there. Yeah. So for clarity. Okay, so yeah, so we have the current going out of the page, and then we try to find a B field outside the wire. So here the red one is the Ampere's loop. In that case, so here, so for the first one, we have an integration of a B dot ds equals mu naught I. So we assume the I is this current, and then due to symmetry, we assume that for a fixed R, the B field is uniform, and then B is also parallel to ds, pointing to the same direction. So in that case, B dot ds is nothing but B times ds. So it becomes this one. Okay. And then as much as B is uniform, we can just put it out. So if you realize it is B times integration of ds. So integration of ds is nothing but the circumference of the circle, so which is 2 pi r. So here we have B times 2 pi r equals mu 0 I. So it turns out to be B equals mu 0 I over 2 pi r. Or here we use the capital R rather than small r. Yeah, it should be small r. It should be 2 pi small r. So here r is used for the radius of the wire. Okay, so for the second case, let me try to draw another figure like this. So this is the radius of the wire, and then here we try to define the so the Ampere's loop is inside the wire. So this is small r. Okay, and this is the Ampere's loop. Ampere's loop. Okay, so here for the left side it is still the same, B times 2 pi r, nothing special. So on the right side, mu 0 I enclosed, we need to determine what is I enclosed. So as much as the current density is uniform inside the wire, so we can write out that I enclosed over a pi small r squared should be the same as I over pi capital R squared. So this is the whole cross-section area of the wire. This is the cross-section area enclosed by the Ampere's loop, and this is the I enclosed, the current enclosed by the Ampere's loop, and this is the whole current. So as much as the J is uniform, so these two ratios should be the same. This is the current density. This is the current density. Okay, so in that case, pi and pi can be cancelled. So we have I enclosed should be I times small r squared over capital R squared. So we make use of this one. So here we have mu 0 I enclosed, which is mu 0 I times R squared over capital R squared. So with some cancellation, we can cancel this R with this R. Okay, so finally we have a B equals mu 0 I over 2 pi, and then here we have R over R squared, so which is actually this one. So we have this one and also this one. So here it means that it is inversely proportional to R, and this is proportional to R. So far, any questions? Okay, so here we have a sample problem. So it says the cross-section of a long conducting cylinder with inner radius A and outer radius B. The cylinder carries a current out of the page, and the magnitude of the current density is the cross-section. In the cross-section is given by J to be this expression with C and R in meters. What is the magnetic field at a point that is 3 centimeters from the central axis of a cylinder? Okay, so yeah, so this is not a perfect circle, it is hollow inside. Yeah, so let's see. Here it asks you the point that is 3 centimeters from the central axis, and the inner radius is 2 centimeters. The outer radius is 4 centimeters. So which means that the Amplus loop is in the middle. Is in the middle. So let's consider what is I enclosed. So I enclosed should be integration of J dot dA. We don't have a circle here because here it is not a closed surface. It's not a closed surface. Okay, so here we try to plug in what is J. J is actually this expression, which is C R squared. C R squared is J. And then for dA, this is a polar coordinate. So for polar coordinate, dA equals R dr d theta. Okay, just keep it in mind. So dA is R dr d theta, and we should have a double integral. Okay, so here we need to determine the lower and upper bound. For dr, we don't integrate from 0 because the middle part is not there. So the middle part is hollow. So yeah, so which means that we just integrate from small a to r. Small a to r. We just make it r, make it a variable rather than fix it to 3 centimeters, so that we can come up with a general solution in terms of r. And finally, we plug in r equals 3 centimeters. And then, yeah, so we have a lower bound to be a, and then upper bound to be small r. And maybe we can just make it like r prime, r prime, d r prime, so that this r prime and this r are different things. Okay, so for the theta, okay, this is the whole 360 degrees, so we integrate from 0 to 2 pi as usual. Okay, so finally we have C, and then integration of dr. So we count, this is r squared, this is r. So we all together have r cubed, r prime cubed, and then we integrate from a to r. And then for d theta, okay, this is 1, but actually we don't need to write it out. We integrate from 0 to 2 pi. So this is nothing but 2 pi. This is nothing but r to the 4th power minus a to the 4th power all over 4. So this is just a polynomial, integration of polynomial. So r cubed so becomes r to the 4th over 4. Okay, so finally this is okay, so finally this is pi over 2, and then c times r to the fourth power minus a to the fourth power. Okay, so this is I enclosed, and then we can really apply Amplus Law. So for Amplus Law, we have a line integration of a b dot ds equals mu 0 I enclosed. So on the left side, as usual, we have a b times 2 pi r, because all the things are symmetric. If this is not symmetric, then you need to spend some time to calculate this line integral. But this is a physics course, not a calculus course, so usually it will be not so difficult to calculate. Okay, so on the right side, it is mu 0 times this thing, so which is mu 0 pi over 2c and then r to the fourth power minus a to the fourth power. Okay, so we have b equals mu 0 let's see, we can do some cancellation first. This pi and this pi can be cancelled. Okay, so that's it. So we have mu 0 and then times c over 4r and then times r to the fourth power minus a to the fourth power. Okay, so so we can just plug in the number. Okay, mu 0 is 4 pi times 10 to the minus 7. So which the 4 can be cancelled, so it turns out to be pi times 10 to minus 7. And then times c is this one. So we have 3 times 10 to the 6th power all over 4 we already counted. So this is 3 centimeters, 0.03. And then we have a 0.03 to the fourth power minus 0.02 to the fourth power. Okay, so this is 20 mu Tesla. And then we also need to determine the direction of the B field. So let's see. So here it says the cylinder carries a current out of the page. The cylinder carries the current out of the page. So here we should have the current going out of the page. And actually here it defines the Ampere's loop to be clockwise. So using the right-hand rule, the current pointing into the page is positive. So because this is clockwise, so you use right-hand rule. Your forefinger follow the direction of the Ampere's loop, and then your thumb pointing into the page. But the current is going out of the page. So in this sense, you should have make this I enclosed to be a negative value. So finally, it is a negative value. And as much as we define the Ampere's loop is clockwise, and this should be a negative value, and which means that the B field is counterclockwise. Okay, B is counterclockwise. Okay, can you follow this argument? So B is counterclockwise. Or actually, you can determine even more directly. It's like the current is going out of the page, so you use right-hand rule, you use your thumb, follow the direction of this current, and then your finger will go in this way, which means that the B field is counterclockwise. Okay. So far, any questions? No. Okay, so let's move on. So here we talk about the solenoid. So it says the magnetic field of a solenoid. The solenoid's magnetic field is the vector sum of the field produced by the individual turns, or we call it windings, that makes up the solenoid. So this is a demonstrative figure of the solenoid. So it's like like this, and then this current is here going into the page. Loop after another loop, and then finally it's go out from here. So and then so this is a more zoom in view, or make the adjacent loop far away from each other, so that you can see what is going on inside. So here we have some observations. So first of all, for the point very close to a turn, the wire behaves magnetically almost like a long straight wire, and the line of B there are almost concentric circle. So for this point, it indicates the B field here, around here, here, and here. So you can see something like the concentric circle here. Okay, so you can feel like, it's like a infinitely long wire. Although this is not an infinitely long wire, but if you just focus on a very close place, then so very long or infinitely long is a relative concept. So if you just zoom into very close to this wire, then you can imagine this is infinitely long. But slightly far away from the wire, then it is not the case. So here we can see some of the concentric circle, and you can also see that. So here this is going into the page, this is going out of the page. For the lower point, here, so the current are going into the page. So you can use the right hand rule to determine the direction is actually clockwise, because if you use you use your thumb pointing into the page, your forefinger is going clockwise. And then for here, this is going out of the page, so you use your forefinger going out of the page, your finger feel like counterclockwise. So you can see the direction of the B field for here and also here. So for the second point, the field tends to cancel between adjacent turns. So it specifies the area somehow like here, and here. So which means that this one is going downward, and this is going upward. So right in the middle, the magnitude should be the same, and they point to the opposite direction. So in the middle of adjacent wire, then the B field is very weak. Both of them are cancelled. And then next, a point inside the solenoid and reasonably far away from the wire, B is approximately parallel to the solenoid axis. So it indicates the parts here. And actually, for the lab, you will do experiment about the magnetic induction. So you need to make use of this so-called solenoid, and then you make use of this part. So here we have a solenoid generating the B field. We will try to consider the B field inside the solenoid is quite uniform. Mostly points to the right side. And then, of course, out of the solenoid, it feels like it will be something like that, okay. So it somehow lies the, yeah, actually it is a magnetic dipole. It is the magnetic dipole. And if you still remember the electric field lines of the electric dipole, yeah, it is somehow like this. But of course at that time it is rotating 90-degree counterclockwise. So its field lines, if we have a electric dipole, the E field line is somehow like this. It's somehow like this. But here also inside the solenoid we have the part with roughly uniform B field generated inside. And of course it will also follow the right hand rule. All the times we will use the right hand rule to determine the direction of the B field related stuff. So here this current is going out, this is going in. So you can imagine the current is somehow like this. It's somehow like this. So you use a forefinger, follow the direction of the current, and then your thumb will point to the right side. Okay, somehow like this. Somehow like this. Okay, you use a forefinger, follow the direction of the current, your thumb will point to the right side, which is the direction of the B field. Okay, so here we also try to quantify the B field generated by the solenoid, and of course we will use the Mps Law to do this stuff. Okay, so this is a cross section of a solenoid. So you can see all these current are going out of the page. All these current are going into the page. So it field lines it go from here to here, and then to the next one, so on and so forth until the end. Okay, so here we try to define a Amplus loop, an Amplus loop which is not circle. So this is an exceptional case. This is a rectangle. Here we also do some approximation, somehow similar to what we did for the capacitor. For the capacitor, we also assume that the E field between the parallel plates are uniform, and then the the E field out of the capacitor is approximately 0, something like that. We also do the approximation similar to that, to those. Here we assume that B is uniform within the solenoid and 0 outside it. Using the rectangular Amplus loop, we can have the following stuff. So this is the original Amplus loop. So, and this is for the closed loop. So from A to B to C to D and then back to A. So on the left side, this is the original line integral. We can separate into 4 parts because we have 4 sides for the rectangle. So we start from A to B, and then B to C, C to D, D to A. So we have A to B, B to C, C to D, and then D to A. So this is nothing special. We just separate this line integral into 4 parts, and then we can determine the values of them one by one. Okay, so for the last 3 terms, let's say B to C. B to C is from here to here. So this is the path, and then B field is pointing to the right side. So for this part, B and DS. Okay, so you can see here, for here, DS is pointing upward, and then B is pointing to the right side. So B dot DS is 0 because B and DS are perpendicular to each other. And then for the outside part, B is 0, so B dot ds is also 0, which means that integration of B dot ds over B to C is 0. Similar for D to A, for this part of B is 0. And then here, B and ds are perpendicular to each other, so B dot ds is 0 either. Okay, so these 2 parts are 0. And then also for this C to D, B field is 0. We are already assumed this case. So the integration for the b dot ds from c to d is also 0. So here we have integration from b to c, c to d, d to a, which means this part, and this part are all 0. So the only remaining terms is actually this one, from a to b. So, and actually from a to b is very straightforward because this is a straight line, and then b is also uniform, and then also parallel to ds. So here ds is point to the right side. So b and ds point to the same direction, which means that b dot ds is actually b times ds. So a and then b times ds, and then b is uniform, so we can put b out, and then integration of ds from a to b is nothing but b minus a, which is the width of the rectangle, or the height of the rectangle. We use h for the width of the rectangle. So we have b times h. So this is nothing but b times integration a to b ds. From a to b ds which is this one is nothing but h. So we have bh here. So on the left side of the Ampere's law, we have b times h, and then equals mu naught I enclosed. So mu naught is a constant. Then we need to determine I enclosed. I enclosed, yeah, everyone is I. So we need to know how many current are there. Okay, so in that case, we don't really know. So at the very beginning, let's try to write it as we have n. We have altogether capital N turn within this length. So here we need to very careful about whether it is capital N or small n. Actually, this equation is small n rather than capital N. So capital N means number of turn, and here small n means number of turn per unit length. So we need to take cautious about whether this is a capital letter. Okay, so here we should have all that. We consider we have total capital N turns for the length of h. So here we have, So here we have a b equals mu 0 I, and then times n over h. So n is number of turn. This is the length. So which means that this is actually mu 0 times I times small n. So this is actually number of turn per unit length, or number of turn per meter for the SI unit. Okay, so here we have a b equals mu 0 In for the b field inside the solenoid. So it relates to so actually mu 0 is a constant 4 pi times 10 to minus 7, and then this relates to the current, how large the current is, and this is the number of turn per unit length, like the density of the turn. Okay, so we finished the solenoid. So here we also talk about the toroid. So the toroid is like you have a solenoid like this, so maybe a longer one, and then you try to connect the front to the end, and then it turns out to be something like this. Okay, so a toroid may be described as a hollow solenoid that has been curved in until its two ends meets. So you touch the front to the end, and then forming a sort of a hollow bracelet 像个手链或者这样的。Okay, so from the symmetry, we see that the line of B forms concentric circle inside the toroid, directed. Yeah. So, and here also this is the toroid, and then this is the cross-section area of the toroid. So you try to cut it like this, so you can see the cross-section area, picture like this. So here, the number of turn here and the number of turn here should be the same. So you can see that for the inner turn, the current are more dense, and for the outer, yeah, this is sparser. So, but as much as the number of turn for the inner and outer turn should be the same. Should be the same thing, because you try to bend the solenoid to be this shape. Okay, so here we try to determine the B field inside the toroid. Okay, and here we try to define the Mps loop to be this orange circle inside the toroid. And yeah, so here we have a current going out. This is the current going in. Okay, so, and actually the only I enclosed only count the inner turns rather than the outer one. The outer turn is out of the loop, so we don't count them as the I enclosed. In that case, for this circle, we apply the Amplus Law. So on the left side, we, as always, have B times 2 by R. And then on the right side, we have μ0 times I enclosed. For each one, it is I. And this is the number of turn for the toroid. So we don't need to consider this number of turn per unit length, because this Amplus loop encloses all the turns. So we have a capital N here. So finally, we have just move these terms over. So we have B equals μ0 I capital N over 2 pi R, like this. Okay, so in that case, B is not a constant. B is not a constant. It is related to the R, and also related to the number of turns, and then also related to the current amplitude. Okay. Okay, so maybe let's have a 10 minutes break first.